the fourth step is attach those semantic rules to corresponding grammar productions. Attach those semantic rules to corresponding grammar productions. Grammar productions. So these are the steps we need to perform for constructing the SDT set. For constructing the SDT, we need to do all these steps. For the given context-free grammar with the given input value, first we need to construct the parse tree. After constructing the parse tree, we need to convert that parse tree into annotated parse tree. Annotated parse tree means a parse tree along with attributed information or attribute information. Attribute is nothing but a type. What type of data it is. Semantic means it tells the type, and syntax means it tells the structure. So after construction of annotated parse tree, we need to compute the attribute information, and the semantic rules need to be framed. After construction or framing the semantic rules, we need to attach those semantic rules to the corresponding productions or grammar productions. So these are the steps we need to do for construction of SDT. So suppose if we take one example, construct SDT that would give construct SDT that would give the output of reduced operations, that would give the total number of reduced output of total, that would give, construct the SDT that would give the total number of reduced actions taken by bottom up parser for the following grammar. So the grammar is E derives E plus T, E derives T, T derives T star F, T derives F, F derives ID, F derives ID. Here the question is, construct the SDT that would give the total number of reduced actions, taken by the bottom-up parser for the following grammar. So here it is very simple, sir. So as we discussed, CFG is given as an input. CFG means context-free grammar. With this grammar, we need to construct SDT. SDT means context-free grammar plus semantic rules. Context-free grammar plus semantic rules. We are having context-free grammar. For these context-free grammar and for these productions, we need to construct or we need to frame semantic rules. We need to frame the semantic rules. For framing the semantic rules, we are having some procedure. What is the procedure? So we have discussed. Construct the parse tree and convert that parse tree into annotated parse tree. After that, compute the attribute information and frame the semantic rules. So these are the things we need to do, sir. These are the things we need to do, sir. So after that, we just attach those semantic rules to the grammar productions. We will see step by step. So for the construction of parse tree with this grammar, we need some string. So here, suppose if I take a string as a plus a star a. So this is the string. For this string, with this grammar, we need to write parse tree. That is the first step. So here he mentioned what he mentioned. Follow bottom up parsing or bottom up parser. Bottom up parser means we need to start at leaves. And we move to the start symbol. We need to move to start symbol from bottom to up. For this purpose, I have started at bottom. Sir. So f can be reduced as a can be reduced as f. A can be reduced as f. And here also a can be reduced as f. Here also a can be reduced as f. Or else, suppose if you want to do step by step, you can also do the step by step process. So in that case, suppose if you want to add in the bottom of parsing nature plus a star a. Here it is the handle, and here it is reduced, f is reduced. After that, I am reducing this f as t. So this is t because f can be reduced as t. id can be reduced as f. id means small a. Identifier. First I reduced a as f, and after that I am reducing f as t. So t plus a star a. So t plus a I cannot reduce. So that's why in the next step t plus a can be reduced as f star a. T plus f. Is there t plus f? No, sir. T plus f is not available. For that purpose, t is reduced as e, sir. E plus f star a. So, 1 minute. Yes. E plus f is not there, but e plus t is there. So for that purpose, e plus t and star a. Suppose if I reduce e plus t, then I will get e star f is not available. For that purpose, e plus t star a is reduced as f, sir. Now t star f can be reduced as t. So t plus e plus t. E plus t can be reduced as e, sir. So I started at leaves and I moved to root. So this is nothing but bottom up passing or RMD in reverse. RMD in reverse. For this, we need to construct the parse tree. So suppose already we know how to construct the parse tree. For the purpose, if we take E plus T, E plus T, and T can be written as T star F4, T star F4, and T can be written as F, E can be written as T, T can be written as F. So these are the things. F means A plus F star and A, and this is also A. So this is the parse tree. This is the parse tree. This is the parse tree. So after construction of parse tree, we need to give the annotations. We need to give the annotations. Annotation means for every non-terminal symbol, we need to give the type. For every non-terminal symbol, we need to give the types. So for that purpose, suppose F can be reduced. F can be reduced when it is replaced with A. Suppose F can be reduced with it is replaced with A. So that's why I'm writing it as F reduce equals to 1. Here also F can be reduced with 1 itself, sir, with A. So that's why F dot reduced equals to 1. Here also F dot reduce equals to 1, sir. F dot reduce is equals to 1. Suppose why I am using reduce? Because in the question itself he has given total number of reduced actions can be taken by bottom up parser. Total number of reduced actions can be taken by the bottom up parser. For that purpose, I am taking reduce, REDS attribute, REDS attribute, RED. Suppose if you want to write reduce fully, you can write it, sir. You can write it. So after that, suppose if we want to reduce T, that can be reduced by replacing F. By replacing F value, we can reduce it. Sir, how can you say T can be reduced by using F? Because we are having the productions E derives E plus T, E derives T, T derives T star F, T derives F, F derives ID. Here F is reduced with identifier A. So it is a simple and it is a single way. And here F can be replaced with T, sir. F can be replaced with T. In the starting classes, I already told you, sir. F derives ID is also equivalent, or we can also write it as F equals to ID. F equals to ID. The left hand side non-terminal is equivalent to right hand side of the production. Right hand side of the production. So we can replace it. So in the same manner, F can be replaced with T, sir. F can be replaced with T. So suppose from A to F, it takes one reduction operation, and from F to T, it is also taking another reduction operation. So for that purpose, T dot reduce equals to F dot reduce plus 1. F dot reduce plus 1. Why? Because suppose F is replacing with T, but for that purpose, here F need to be reduced with A. Here it is having 1. Again, it need to be reduced with, it need to be replaced with F reducer. For that purpose, I am writing T dot reduce equals to F dot reduce plus 1. F dot reduce plus 1. And here also the same, sir. And here also the same, sir. T dot reduce is equals to, here F is replaced with A and T is replacing with F. Here it is one reduction action, here it is one reduction action, and here it is another reduction operation. So for that purpose, we can write it as F dot reduce plus 1. F dot reduce plus 1, sir. F dot reduce plus 1. After that, to reduce E can be replaced with T, sir. E can be replaced with T. So for that purpose, I can write it as E dot reduce equals to T dot reduce plus 1, because here one more reduction operation is there. Up to T, this one, sir. After that, one more reduction operation we need to do. That's why T dot reduce plus 1. T dot reduce plus 1. And here the T dot reduce equals to, we need to replace this value plus this value and add one more. So for that purpose, T1 dot reduce plus F dot reduce plus 1. T dot reduce plus F dot reduce plus 1, sir. Sir, what is T1? Here we are having T and T. For the differentiation between this T and this T, I am writing it as T1, sir. I am writing it as T1. So this is also T only, not T1. This is not different from this T. For doing the specification for this T and this T, I am writing as T1 for this one, sir. And after that, here E dot reduce is equals to E1 dot reduce. E1 dot reduce means this one, sir, plus T reduce. T reduce means this reduce, sir, plus 1. So this is the annotated parse tree. This is the annotated parse tree. For the given parse tree, I have written the annotated parse tree, sir. For the given parse tree, we are converted annotated parse tree. The parse tree is E plus T star F A T F A. So this is the parse tree, and for this parse tree we have written annotated parse tree. So for writing the annotated parse tree, we need to consider what is given in the problem. In this given problem, he mentioned construct the SDT that would give the total number of reduce actions. How many number of reduce actions are required to move from leaves to root? For suppose, if we see here, it is 1, sir. And it is 1, sir. From here to here, T dot reduce is equals to F dot reduce plus 1. F dot reduce, what is the value? Reduced value 1. 1 plus 1, 2, sir. Here also F is reduced with T. That's why this is also 2, sir. So after that, it is T can be replaced with E. For that purpose, one more reduction operation is there. So E is 3, sir. Here it is 2 and here it is 1. This means T1 plus F plus 1. That means 2 plus 1 plus 1. that is equals to 4, sir. Here this means E1 plus T plus 1, sir. E1 means 3 and T means 4 plus 1, sir. So totally, how many number of reductions are there, sir? For the given input, the reduction operations are 8. For the reduction operations are 8 at root. 8 at root. For the root, 8 reduction operations are required for the given input string for the given grammar or context-free grammar. So 2 steps are completed till now. 2 steps are completed. Construction of parse tree completed. Construction of annotated parse tree also completed. Now we need to frame the semantic rules. We need to frame the semantic rules with attribute information. We need to frame the semantic rules with attribute information. So what are the semantic rules we can frame? Suppose if you see here, f dot reduce is equals to 1. So the semantic rule for f dot reduce equals to 1. So this is one semantic rule. For reducing f, we need one reduction operation. That is sufficient. After that, to reduce t, t dot reduce equals to f dot reduce plus 1. Sir, how can you write this one? F dot reduce plus 1. Suppose if you see here, to reduce t, we need f dot reduce plus after that, to move from here to here, one more reduction is required. That is plus 1, sir. That is plus 1. So for that purpose, I can write it as t dot reduce is equals to f dot reduce plus 1 and e dot reduce equals to e dot reduce. This is for t derives f, sir. This is for t derives f. This is for f derives id. This is for f derives id. And e dot reduce is equals to t dot reduce plus 1. T dot reduce plus 1. So this is the thing, sir. This is for e derives t. So we have completed 3 productions. Out of 5. This is completed. For these 2, we need to construct the semantic rules. For those, t dot reduce is equals to what are the things here, sir? T dot reduce is equals to t1 dot reduce plus f dot reduce plus 1. T dot reduce plus t1 dot reduce plus f dot reduce plus 1. t1 dot reduce f dot reduce plus 1, sir. So here this t both are same, sir. But for the differentiation, because this t is different, this t is different. This t is calculated from this one. So for that purpose, I am giving just a notation as t1. I am giving the notation as t1. This is for t derives t star f. T derives t star f. This is also completed. And finally, e dot reduce is equals to e1 dot reduce plus t dot reduce plus 1. So here e1 dot reduce, t dot reduce plus 1, sir. This is for e derives e plus t. These are the semantic rules with attributed information. Semantic rules. So the third step also completed, sir. Here we framed the semantic rules. Here we framed the semantic rules. For these semantic rules, we need to attach these semantic rules for the given grammar. The given grammar is E derives E plus T, E derives T, T derives T star F, F derives, T derives T derives F, F derives ID, F derives ID. The semantic rules for these, are yes, sir. So what is the semantic rule for F reduce? For this one, F dot reduce equals to 1. So this is F dot reduce equals to 1, and T dot reduce is equals to F dot reduce plus 1, and T dot reduce equals to T1 dot reduce plus F dot reduce plus 1, and E dot reduce equals to T dot reduce plus 1. E dot reduce equals to E1 dot reduce plus T dot reduce plus 1. So all these semantic rules are these only, sir. These only. Just I am attaching the semantic rules to the productions. Just I am attaching semantic rules to the productions. These are the context-free grammar productions, and this is the rules, semantic rules for corresponding productions. By adding these two, we can call this one as SDT. SDT is nothing but context-free grammar plus semantic rules. Context-free grammar plus semantic rules is nothing but syntax directed translation. So for the construction of syntax directed translation or SDT, we need to check what is the criteria. Here the criteria is reduced actions. In the same manner, he will give some criteria. With that criteria, we need to construct the SDT. After constructing the SDT, we can check, is it satisfying with those rules? Is it satisfying or not, like that? To construct the parse syntax directed translation, we are having 4 kind of steps. First step is we need to construct the parse tree. After that, we need to construct the annotated parse tree. After that, we need to construct annotated parse tree. After that, we need to frame the semantic rules. After that, we need to frame the semantic rules. After that, we need to attach those semantic rules to the grammar productions. After that, we need to construct those semantic productions to the grammar productions. So this is the way for the construction of syntax directed translation or SDT. Suppose if we see construction of SDT for the same grammar with a different criteria, we will see one more problem, sir. We will see one more problem. Construct SDT to calculate height of the parse tree. Height of the parse tree where height is attribute. Write the semantic rules. Write the semantic rules for the given productions. For the given grammar 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 productions. So same grammar, sir. Same grammar. E derives E plus T. E derives T. T derives T star F. And T derives F. F derives ID. F derives ID. So this is the context free grammar given, but here the difference is attribute is different. In the previous problem, the attribute is reduction action or reduced action. Based on the reduced action, we need to consider the type or attribute. But here the attribute is height. Attribute is height, sir. Attribute is height. Suppose if we are having any tree, so the height can be calculated as, for example, E derives E plus T F A. Now the height of this tree is, we can write it as for the given string A plus B, A plus A, I have constructed the parse tree for the same grammar. So suppose if you check the height, so this is 1 and 2, 3, and this is 4, sir. The height of the parse tree for construction of this string with this grammar, the height is 4, sir. For that purpose, in the same manner, we need to construct the parse tree for the given string. After that, we need to give the annotations, that means attributes to the parse tree. After that, we need to construct the semantic rules. So how we are constructing semantic rules for the given grammar with the given string, we will see, sir. So here the string is also same, sir. A plus A star A. A plus A star A. So here also the parse tree is same. Parse tree is same. E plus T and T star F A T F A. So this is the thing, sir. For this string, we need to construct the annotated parse tree. So for that purpose, the same parse tree I am taking, sir. A plus T and T, F, A. And for this, I am writing it as T star F. So F, A, A. So this is the thing, sir. This is the thing. For this, now we need to try to write the annotations. Now we need to write the annotations for these. The annotations can be written with the help of attribute height. With the help of attribute height. So we'll see. F dot ht equals to, I can write it as 1, sir. F dot ht is equals to 1. Sir, why you are writing 1? Suppose if you take this construct, the height from, suppose here f is the root, sir. Here f is the root and a is the leaf. So from root to leaf, there is only one edge. There is only one edge. So the height from root to leaf is 1, sir. For that purpose, I have written f dot ht equals to 1. F dot ht equals to 1. And here also f dot ht equals to 1 because the edge is only 1. And here also the edge is only 1. F dot ht equals to 1. I am giving the attribute for the grammar production symbol. By giving attribute information to the grammar production symbol, we can call that one as annotated parse tree. So here these are completed, sir. Here these are completed. For these, suppose if you take this thing, now the height of t ht equals to, here to here the height is 1, sir, and from here to here one more edge is there. That's why I can write it as f dot ht plus 1. F dot ht plus 1. This is f dot ht. This is f dot ht. So after that, there is one more edge between f to t. That's why I am adding f dot ht plus 1, sir. F dot ht plus 1, sir. So further, after that, here t dot ht is equals to, here also the same thing. Here also the same thing. F dot ht plus 1, sir. F dot ht plus 1, sir. F dot ht plus 1 t dot. Now, if I construct e dot ht is equals to t dot ht plus 1. 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 For this, here there are two ways to reach to leaves. There are two ways to reach to leaves. One is this path. Another one is this path. Another one is this path. Suppose if we see this path, 1, 2. Height is 2, sir. Suppose if you see this path, 1, 2, 3, sir. So height is 3, sir. When there is more number of paths from root to leaves, then we take the maximum path, the maximum value as the height, So in the same manner, for the calculation of t, I'm writing it as t dot ht equals to maximum of T1 dot ht. Here this is also T, this is also T, sir. That's why I'm writing it as T1 dot ht, comma f dot ht, f dot ht. After that, if you come to here or here, there is one more edge is there to move to ht. For that purpose, plus 1 maximum of T dot ht and maximum of T dot ht comma f dot ht plus 1, sir. So this is the attribute information here. Suppose if you want to write here, E dot ht means here there is a path and here there is a path and here there is a path. From these three paths, here we are having the maximum value here. So for that purpose, E1 dot ht, sorry sir, maximum of these two, we need to calculate maximum of these two. So for that purpose, we need to write it as maximum of E1 dot ht, comma, here this is T dot ht plus 1 plus 1. So this is the thing, sir, for construction of maximum height. For example, if we take this height is 1, this height is 1, this height is 1, and here it is f plus 1, 2, and here it is f plus 1, 2, and here it is maximum of T f. So maximum is T, sir. 2 plus 1, that is equals to 3, sir. 2 plus 1, that is equals to 3, and here it is 3, sir. Maximum of 3 comma 3, maximum of 3 comma 3, 3, sir, plus 1, that is equals to 4. So the height of this sparse tree is 4. So we will check it. So it is 1 and it is 2 and this is 3 and this is 4. The height of this sparse tree is 4. The height of this sparse tree is 4. Manually we calculated along with rules also we calculated. We have calculated. Suppose now if we write it as the semantic rules, and directly I am writing, sir. Semantic rules are directly I am attaching to the productions. The productions are the given productions are E derives E plus T, E derives T, T derives T star F, T derives F, F derives ID, For all these, we need to write semantic rules. What is the semantic rule for F1 or F? F dot H is equals to 1. So we can write it as F dot HT, height. For height, I am taking HT, sir. If you want to write full form, you can write height. So F dot HT equals to 1. And next, T dot HT is equals to F dot HT plus 1. T dot HT equals to F dot HT plus 1. T dot HT equals to maximum of T1 dot HT comma F dot HT plus 1 plus 1, sir, plus 1. Here E dot HT equals to T dot ht plus 1, t dot ht plus 1. And finally, e dot ht equals to maximum of this one and maximum of this one. Maximum of e1 dot ht comma t dot ht plus 1, sir. Plus 1, sir. This is the given context free grammar, sir. This is the given these are the semantic rules. Semantic rules. By adding these two, we can call it as SDT. By adding these two, we can call it as SDT. So these are the things, sir. These are the things. So construction of SDT. Construction of SDT. So this is the way for constructing SDT for the given context-free grammar and the string. With the string and the context-free grammar, we can construct SDT by writing the semantic rules. So this is the procedure, sir. For the purpose, first we are writing the parse tree. For that parse tree, we are giving the annotations. So then it is converted as annotated parse tree. After that, we are framing the semantic rules with that annotated parse tree. For that annotated parse tree. After that, we are constructing the SDT by attaching semantic rules to the corresponding context-free grammar productions. Context-free grammar productions. So this is the way for construction of SDT. So this is the one kind of question, sir, you may get in GATE examination, or you can get the question as like this also. You can get the question as like this also. Take an example. Consider the following SDT. Consider the following SDT. S derives capital AS. S derives AB. A derives small a. B derives small b, capital C. And capital B derives small d, capital B. And capital C derives small c. Small c. So here the questions are, question number one. This SDT is carried out with this SDT is carried out with bottom up parser, sir, BUP, bottom up parser. Then what output it produce? What output it produce? For input. A, D, B, C. A, D, B, C. And second question. This SDT is carried out. This SDT is carried out with top-down parsing, TDP, top-down parsing. Suppose if this SDT is carried out with top-down parsing, then what output it produce for input A, D, B, C. So this is the question, sir. So here SDT is given. Sir, only constrigram is given, sir, not SDT is given, sir. Sorry, sir. I have not written the remaining part. I will write it here. The remaining part is also given, sir. Print 1. Print 2. Print 3. Print 4. Print 5. Print 6. So these are the semantic rules, sir. Conditional grammar is there and semantic rules also there, sir. Just all are print 1, print 2, print 3, print 4, print 5, print 6. So SDT is given, and questions are there. Follow bottom-up parsing and follow top-down parsing, and try to accept the given string. What is the output? So these are the questions. Given, sir. Before going to solve these questions, just we'll see some points. If any SDT, if SDT is note these points, sir. Just take note. So with these notes, we can solve the problems. If SDT is carried out with bottom-up parsing, bottom-up parser or bottom-up parsing for every reduce action, the semantic rule attached to the corresponding production will be executed. What he is saying is, suppose if we reduce AS as yes, then you need to execute this. That means you need to print 1. Suppose if you use AB as, if you replace AB as yes, then you need to print 2. So in the bottom-up parsing, suppose if you use bottom-up parser or bottom-up parsing, then for every reduction or simply for every handle, you need to execute the corresponding semantic rule. In the same manner, if this is the bottom-up parsing. For this is the bottom-up parsing, sir. This is the bottom-up parsing. Suppose if you take top-down parsing, the simple thing is SDT is carried out with TDP, not television party, sir. It's a TDP means top-down parsing, or BOP, bottom-up parsing. SDT is carried out with TDP or bottom-up parsing, or top-down parsing or bottom-up parsing. Parser sorry, output is same for the same input, for the same input, Suppose if you take the same input, for top down parser and bottom up parser, then the output is also same. So for that purpose, in the examination, suppose if you calculate it, if you get something as an output, suppose something to something you like, so then that is the same result is applicable to the top down parsing. No need to calculate separately. But I will explain you how to calculate separately with the top down parsing. So what is the procedure we need to follow? But in the examination, so you no need to calculate it for both. If you get an answer for the bottom up parsing, you can use it for the top down parsing. Suppose if you get the answer for the top down parsing, you can use it for the bottom up parsing. How it is possible, sir? So there is a one rule. The rule is, if SDT is carried out bottom up or top down, whatever it may be, for the input, for the same input, output is same. For the same input, output is same. For that purpose, no need to calculate those two. So that is the thing, sir. And next one is how to calculate the output or execute the semantic rules for the top down. So if SDT is carried out, yes, SDT is carried out with top down parsing, then semantic rules are executed in DFS traversal order. Depth first search. So you may learn this topic in data structures or design analysis and algorithms, how to construct the DFS by using stack, like different manners. Without stack also there, sir. With stack is also there, but we use the stack there. So by using DFS or depth first traversal, we can execute the semantic rules in the case of top down parser. So, and one more condition is there, sir. That should be left to right. Depth first traversal order from left to right. So these are the things, sir. Before going to solve the question, we need to know these three things. One is to do with bottom up parsing. Every semantic rule can be executed at the time of reduced action. Suppose if it is a TDP, that means top down parsing. So we need to use DFS. Okay, sir. We will check it. For bottom up parsing, the given input is A, DBC. DBC. So here the given grammar is S derives AB, A derives small a, B derives small bc, B derives db, C derives small c. So to reduce any symbol of the production, we need handle. We need handle. So C is not there here, so it is not possible. DB is also not there. BC is also not there. Small a is there. Small a can be replaced with A, sir. Small a can be replaced with A. Small a can be replaced with A, sir. So for that purpose, I am using A. I am using A, D, B, C. So here I reduced. Which one I reduced? This one. This one. What is the semantic rule there? What is the semantic rule there? Print 3 at the time of reducing capital A with small a, then we need to print 3, sir. We need to print 3, sir. So I have taken 3. After that, AA is not there. C is not there. DB is not there. C is there. Only A is there. AA is also not there. AS is also not there, sir. AB also not there, sir. So that's why again I am using A, sir. So here remaining part is already there. A, D, B, C. Here also I reduced the same. That's why one more 3 is added. For this 3, one more 3 is also added, sir. Now I am reducing this A. So A is same. D, B, C is also same. So here one more A I am reducing. One more A I am reducing. That's why I am writing it as 3, 3, 3. So this means print 1. This means print 2. This means print 3. This means print 4. This means print 5. This means print 6. These are the semantic rules given. When I am using this one, I am writing or I am printing 3. So in these 3 cases, I am reduced small a with capital A. That's why I used these are in this order, sir. In this order. In this order. After that, here A is not there, sir. A is not there, but I can replace with C as capital C. I can replace C as capital C, sir. So because there is no handle, A is not a handle, AA is not a handle, AA is not a handle, ADB is not a handle, AD is not a handle, DB is not a handle. So from left to right, there is no handle. So the handle here is handle or proper handle. Proper handle means we must move to the, it helps to reach the root from leaf. That can be called as proper handle. Here the proper handle is A, D, B, C, capital C. Small c can be replaced with capital C, sir. So now capital C can be replaced with, small c can be replaced with small capital C. Here the product semantic rule is 6. That's why we can write it as 3, 3, 3, 6. 3, 3, 3, 6. I am printing 6. I am printing 6. Now, so here A is not there, AD is not there, but BC is there, sir. BC handle is there. For that purpose, A, D, BC means capital B. BC means capital B. That's why I'm writing it as B. So B can be replaced with small b, capital C. So that's why 4, sir. 3, 3, 3, 6, 4. 3, 3, 3, 6, 4. Now DB is there. DB can be replaced with again B, again B, again B, sir. A, B, B, sir. So now this is 5. 3, 3, 3, 6, 4, 5. 6, 4, 5. AB can be replaced with yes. Yes. Now 3, 3, 3, 6, 4, 5. So AB can be replaced with 5. That is 2, sir. Now AS can be replaced with yes. Yes. 3, 3, 3, 6, 4, 5, 2, 1, sir. 5, 2, 1, sir. Again, AS can be replaced with A, sir. So that is also print 1. 3, 3, 3, 6, 4, 5, 2, 1, 1. So this is the output. This is the output by using bottom-up parsing. What is the output? 3, 3, 3, 6, 4, 5, 2, 1, 1. So this is the output. So what is the question he asked? What is the or what output it produced for this input? For this input, the output is 3, 3, 3, 6, 4, 5, 2, 1, 1. 2, 1, 1, sir. 6, 4, 5, 2, 1, 1. So simply we can write 3, 3, 3, 6, 4, 5, 2, 1, 1 is the output of the question top-down parser with the input A, D, B, C. For this question also, the answer is same, sir. The answer is same. For this, you no need to calculate for bottom up and top down because there is a rule. What is the rule? If the input is same, for that SDT, output is also same. For that purpose, we can simply tell the output is 333, 645, 645, 211. Sir, suppose if they give the question, what is the output with the top-down pass? What we need to do, sir? So with the top-down also we can calculate. There is a procedure. What is the procedure here? SDT is carried out with TDP, top-down parsing. Then the semantic rules are executed using DFS traversal order. So we can easily write the things, sir. Suppose for that TDP, suppose if you take TDP, top-down parsing. So we need to start at top-down. That's why we need to start at yes, sir. S can be written as A, yes. A can be written as small a. Again, S can be written as A, yes. A can be written as small a. Again, S can be written as A, B. So A can be written as small a. B can be written as D, B. And again, because 3S, what the input? A, D, B, C. I need to check it. A, D. Again, D, B, capital C. Capital C means small c. So A, D, B, C, sir. So this is the input. Sir, okay, good. Sir, 3, 3, 3, 6, 4, 5, 2, 1. How can you get this output from this one, sir? How can you get output from this one, sir? We'll see it. So after construction of the parse tree, first we need to construct the parse tree. After construction of the parse tree, we need to start at root, sir. We need to start at root. So from root to here I came. From root to here I came, sir. So from root to here I came. Here it is non-terminal. Is there any child for this? Yes, there is a child. So move to that child. Is there any child for this? No. No child is there, sir. No child is there, sir. So again you need to check what is there any right hand child for this? No right hand child for this. So you move to leaf, and again you move to parent. Again you move to parent. That's why this is completed. This is completed. For that purpose, here it is completed. So here the grammar is A derives small a. So A derives small a means 3. We need to replace it with 3, sir. So we have written 3, sir. After that, is there any right hand side? No, sir. It is moved to next. Yes, left hand side completed. Yes, right hand side. Sorry, left hand side completed. We are moving to yes, right hand side. That means sibling of A. Sibling of A. From here to you move to left, because he mentioned depth first traversal from left to right. Depth first traversal from left to right. That's why I moved to A. From A to that child, small a, no child. That's why again I moved to parent, not a root, sir, parent. Here there is no left right child. That's why I moved to left, and again I moved to parent. I moved to down, and that means child, and I moved to parent. Child parent completed. Child parent completed means this is completed. That's why again I am writing 3, sir. Now again sibling. Here I moved to A. From A to A to A. Here also I am moving from child to parent. Child to parent. No right child for A. So that is completed. That's why again I am writing 3, sir. Again I am writing 3 here, sir. Now I am moving to B. Here I am moving to sibling of A, that is B. Now I move to D. From D to B. But here it is not completed. Because right child is there. Right child is there. So the work of B is again existed. The work of B is again existed. So for that purpose, I am moving to B. Here from B to small b I moved, and small b to again capital B I reached. Here also there is a right child. So again I am moving, and here I am moving to C, and C to capital C. Here now small c can be reduced with the capital C, because there is no right hand side production. So small c means that is 6. That is 6. This is completed. Now we are at capital B, and the childs are small b, capital C. Capital B derives small b, capital C. The production is this one, sir. That means 4. So this is completed. Now, sorry, sir. This is completed. Now I move to again this piece, sir. Now small d, capital B. So small d, capital B means 5. So here I am using 5. This B is also completed, sir. Now I am moving to yes, sir. Capital A, capital B. Capital A, capital B. Capital A, capital B means P2. print 2. Then I am moving to here. Capital A, capital S. The chains are capital A, capital S. So capital A, capital S means 1, 1. Capital A, capital S means 1. Again, I move to here, sir. So here it is also left child is capital A, right child is capital S. AS means 1, sir. Now check it. So both are same. Both are same. So that's why what I'm telling is for the given SDT, the output of top-down parser and bottom-up parser for the same input, output is same. Output is same, sir. Output is same. So with this also you can get the questions, sir. You can get the questions. These kind of questions also you can get. So previously one question is asked. The same manner, previously one question is asked, previous gate question, sir. So that is previous gate question. Consider the following. Consider the following SDT, syntax directed translation scheme. SDT, yes, syntax directed translation scheme. Syntax directed translation scheme with non-terminals S comma A and terminals small a comma small b. Small a comma small b. The SDT is S derives small a capital A, S derives small a, capital A derives capital S small b, sir. Here the semantic rule is print 1. Here the semantic rule is print 2. Here the semantic rule is print 3. The question is using the above SDTS, the output printed by a bottom-up parser for the input A, B is option A 132, option B 223, option C 231, option D syntax error. By seeing the question itself, you can say this is not correct. Why? Because, sir, in the semantic analyzer, we don't get the syntax errors. So one of the answer is there. Sir. Here he mentioned not a semantic error. He mentioned a syntax error. So syntax error is already cleared by the syntax analyzer only. Then only we will move to the semantic analyzer. And SDT can identify the semantic errors, not the syntax errors. Even though there is a syntax error, it cannot be identified by the SDT or semantic analyzer. So syntax error is not the correct answer. Some answer is there. So because for giving some confusion to you, so they may ask questions like this, some different manner. So like this only, he give this option here. So okay, good. bottom up parser he mentioned, and the input is AA B cell. AA B cell. AA B cell. So suppose the grammar is S derives and S derives small a and A derives SP. Sir, in the initial stages at the time of writing bottom up parsing or top down, at the time of we are doing top down parsing, bottom up parsing, I clearly mentioned you handle is different from proper handle. Handle is different from proper handle. Proper handle means it allows us to move from leaves to root. Leaves to root. Sometimes some handles not allows us to move to from leaves to root. For example, if you see here, A can be replaced with S, S-A, B, S-A, B. Is there any SA here? Is there any SA here? So, okay, SS, B. SB is there. S, A is there. Is there SA to reduce? No, sir. So, that's why this is not the proper handle. This is not the proper handle. We should not take this one as a handle. So here AAB. I am taking this one as handle here. A B. Now if we replace SB, SB can be replaced with capital A. Small a and SA can be replaced with yes. So this is the way for the constructing the bottom up parsing. So this is not a correct way because it is not proper handle. Here replacing A with S is not the proper handle. Okay, good. Here I have constructed parse tree. Now the question is, what is the output for the input? So already we are having the rule for the bottom up parsing. At the time of reducing, we need to execute the semantic rule. So for that purpose, here I am reducing. So the semantic rule for this is, so this is print 1, this is print 2, and this is print 3. So small a is replaced with capital S. That means this production is used. That means I need to print 2. Now here I used this one. A derives capital S small b. That means 3. After that, small a, capital A can be derived by S. That means 1. So first we need to check, is there this option in our given question? 2, 3, 1. Yes, there is 2, 3, 1. So option C is correct one. Sir, why not A and B? So you can check it, sir. So 2, 3 means, first of all, we need to reduce 2. Reduction of S means this one, sir. So this one. Reduce 2. But after that, reduction is not there, sir. After that, reduction is not there, sir. 3 reduction is not there, sir. That's why it is not correct. And one more option is there. 1, 3, 2. 1, 3, 2 means S can be replaced with A, capital A. So that is also not possible because A is there. A is. For reducing S, A. So I don't have A is capital A. So that's why that is also not possible. That's why option C is correct for the given input. Option C is correct for the given input, sir. So for the construction of SDT and for finding the output for the given SDT. So these two are discussed, sir. Different kind of problems also we solve. So if anyone are having doubts regarding the construction of SDT and for finding the output for SDT, so you can ask, sir. If you are having doubts regarding SDT, in the SDT, mainly we discussed two things. One is how to construct the SDT. Another one is how to calculate the output for the given SDT. These two things we have discussed, sir. With the SDT, you will get the questions on those. So you can ask any doubts regarding SDT. Okay, sir. Correct. Great. Next point is we are discussing about attributes. Sir, how many kind of attributes are there? There are two types of attributes are there, sir. One is synthesized. Attribute. Another one is inherited attributes. One is synthesized attributes. Another one is inherited attributes. Sir, when we call the attributes are synthesized attributes, when we call the attributes are inherited attributes. Suppose if you take synthesized attributes, the attribute value of a node, for every node we are calculating attribute value. Suppose if you see here, this is the node. For this we calculated attribute value. Here it is a node, calculated attribute value. For any node, if we calculate attribute value for that node from its children, calculating attribute value from its children, then we can call that one as synthesized attributes. Then we can call them as synthesized attributes. Suppose if we calculate attribute value for any node, then we can call that one as synthesized attribute. Otherwise, if we calculate attribute value from its parent or left sibling, then we can call it as inherited attributes. Sir, there are two different kind of attributes. One is synthesized attribute, another one is inherited attribute. Sir, what is attribute? Attribute is nothing but it tells the type. It tells the type information. It is associated with grammar production symbols. These attributes are computed, or these attributes are categorized as two types. One is synthesized attributes and other one is inherited attributes. From this topic also we will get the questions on gates from the synthesized attributes and inherited attributes. So how we categorizing synthesized attributes and inherited attributes is inherited attributes means we are computing attribute value. We are computing attribute value from its parent, from its parent. Suppose if you take A derives BC. So this is the parent. From this parent, if we calculate attribute values of these B or C, so then we can call it as inherited attribute. Or else from B to C also we can calculate it. The attribute value of C can be calculated from B. The attributed value of C can be calculated from B. From left sibling or from parent, we can call it as inherited attribute. Inherited attribute. Suppose synthesized means if we calculate from children, BC are the children of A, because we can write it as BC. So from B and C we are calculating the attribute value of A, attribute value of A from C or from B also. So then we can call that one as synthesized attribute. Any attribute value is calculated. From its children. That is called as synthesized attribute. Suppose if we calculate any attribute from its parent or from its left sibling, then we can call it as inherited attribute. For example, S derives TL, T derives int, L derives L comma ID, and L derives ID. This is the context free grammar, sir. This is the context free grammar given. So now we need to first construct the SDT. That means semantic rules. For constructing semantic rules, we need some string. Here the string is int A comma B comma C. So this is the given input. By writing parse tree for this, I will get it as S derives TL. T means int. L means L comma ID. Again L means L comma ID. Now LD means ID. So this is the parse tree. Now if I calculate the attributes, how we are writing the attributes, how we are writing the attributes. Now, this is the child. Suppose if you take this, T can be replaced from its child. T can be replaced from its child. T can be calculated or computed. The value of T can be calculated with the child. So that's why I can write it as T dot S type. T dot S type is equals to int. That means this is the synthesized attribute. The type of T is calculated from its child. Here I mentioned calculation of attribute value from its children. Is called as a synthesized attribute. That's why this is a synthesized attribute. And now, so L can be calculated with T. L can be calculated with T. How can L can be calculated? T, sir. Here there is a production. T is the left child or left value, left sibling for L. So with T, I can replace L dot I type. L dot I type equals to T dot S type. T dot S type means int. T dot S type means int. From this L, we can calculate this. From this L, we can calculate this one. From this L, we can calculate this one. From this L, we can calculate this one. So, parent to child. Suppose if it is the parent to child, what we can call, sir? From parent to child. Suppose if we calculate the attribute value from its parent, that is called as inherited. So that's why I'm writing here it as L dot I type equals to int, or else we can write it as L dot I type equals to L1 dot I type, because this is the L1, this is the L, sir. Here also L dot I type equals to int or L1 type, like this, sir. So this is no need to calculate, because this is the terminal, this is also terminal, sir. For that purpose, we can write them as add type. Just we add type. From this, we are adding type. Here, we are having one function, that is add type. This inserts the type of the value in the symbol table. The type of that variable is inserted into the symbol table, sir. So this is the thing. Now if we check, this is the synthesized. This is the synthesized attribute, and this is the inherited attribute, and this is also inherited, because from parent to it is calculated. It is also inherited. This is inherited, and this is add type. This is add type function. So this is the way, sir, for checking that is synthesized attribute or is it synthesized attribute or inherited attribute? Is it synthesized attribute or inherited attribute? So synthesized attribute means, suppose if we calculate from children to its parent, or parent attribute value is calculated from its children, parent attribute value is calculated from its children, then we can call it as synthesized attribute. Otherwise, if we calculate its attribute value from its parent or left sibling, sir, why not the right sibling? Sir, suppose if any time, if we write a tree, we fill from left to right. If there is a right, then left is compulsory existed. But if there is a left is existed, right child or right sibling may exist or may not exist. That is not a mandatory. So if there is no value, how can we calculate it? So that's why from given parse tree or from the given context free grammar, we calculate the inherited attributes with parent or left sibling only, not from the right sibling. For example, if there is c dot x, we can't calculate b dot x from c dot x. It is not possible. It is not possible. Left, right child or right sibling cannot compute the left sibling. So that's why that is not possible. That is not possible, sir. So these are the types of attributes. So how to calculate, how to find the attributes? Is it an inherited attribute and synthesized attribute also? We discussed it, sir. So in the next class, I will explain you S attributes and L attributes and how to calculate S attributes and L attributes. That is also very simple, sir. S attribute means SDT that uses only synthesized attributes. Suppose if you use it, if there is any SDT, if you take any SDT that is having only synthesized attributes, that is called as S attribute. S attribute. Suppose if it is having synthesized plus inherited attributes, SDT having synthesized plus inherited attributes, that is called as in L attributes. That is called as L attribute. For example, if you take this example, if the same example, this is L attribute because inherited attribute is there, synthesized attribute is there. But in any SDT having both, that is called as L attribute. L attribute definition. That is called as L attribute definition. Sir, I discussed about you. I discussed attribute, synthesized attribute, inherited attribute, S attribute definition, and L attribute definition. Attribute is nothing but it tells the type information, and in that there are two categories. If we calculate attribute value from its children, those kind of attributes are called as synthesized attributes. Suppose if we calculate attribute value from its parent or left sibling, then we can call that one as inherited attribute. Suppose if any SDT from the given grammar or SDT is nothing but CFG plus semantic rules. In this, all productions are synthesized attributes. Then I can call that one as S attributed definition, or else it is a combination of inherited attribute plus synthesized attribute. I can call it as L attributed definition. Then I can call it as L attributed definition, sir. So I will explain you some questions on this L attribute and S attribute in the next class, sir, in tomorrow's class. So from these discussed topics, if any one of you having doubts, please ask, sir. Otherwise, I will close the session. From SDT, construction of SDT, and calculating the output value from the given SDT, attributes. Two kinds of attributes are there: S attribute and inherited attribute. So, and with these only S attributes are there, or sorry, synthesized attributes are there. Then I can call as S attributed definition. By combining by any SDT having a synthesized and inherited, that is called as L attributed definition. So from all these topics, if any one of you are having doubts, please. Okay, sir. If you don't have any doubts, I will close the session. Okay, sir. Thank you.